List all extrema and state at what x value each extremum, that's the singular, is located. So what did you say about this point? Oh, it works. Yay. This point at x equals -5. What is that? Is that anything? No, nothing. So nada, nothing. Okay. How about this point at x equals -3? Is that anything? What do we think? It's a maximum? What kind of maximum? Relative. Good job. So this is a relative max. So I'm going to say there's a relative max at x equals -3. All right. How about x equals -2? What do we call that? -2. Sorry, my technology is catching up. Nothing, you think? I think it's something. It is a minimum. What kind of minimum? It is a relative. Because is it the lowest point in the entire function? No. So it is a relative. So I would say relative min. I'm okay with you abbreviate at x equals -2. Yes. Yeah. And did you catch the other day where I said you could have two of the same or more, like more than one of the same absolute? If think about the sine function, right? What's the max like height of it? Like if that's like, let's say that's like 1, right? The max height is 1 at multiple locations. So it still has more than one absolute. That's okay. Okay, and minimums. All right, so then that's relative min. How about this guy up here? What is that? Relative max. Okay, so I would say relative max at x equals 1. Okay, and then what about x equals 3? No, because it's a discontinuity, a jump discontinuity, right? That's nothing. And so do you see like this is a hole, right? So at this point, this is a hole, and it doesn't exist on f of x. Okay? But if this hole, so this is actually nothing. It's not an absolute min because it's a hole, right? There's no function there. So there's actually no absolute min for this function because you can have infinitely many fractions in between here. So you can't, there's no absolute min. What if this was filled in? If at x minus or x equals 3, if it was a closed dot, then it would be an absolute minimum, okay? But we couldn't take the derivative there because there's a jump. Okay, that's the difference. How about this up here? At x equals 4? It can be something if it's an endpoint and closed. It just can't. If it's an absolute max, it can be something. But it couldn't be, what you were hinting at is it couldn't be a relative max or min on your endpoints, right? So that's why the one at x equals -5, right, is nothing, because we can't call that relative because I actually don't know what's happening to the left of it to say if it's relatively the lower point or not, okay? But I can have an absolute max on an endpoint, yes.
And it's not absolute because the hole is lower than that.
It's what is not absolute for at x equals -5?
X equals 3.
At x equals 3. That's nothing.
Or it's because there's still more like this.
No, because so because I have the rest of this function, the minimum value here could be like -1.5, -1.6, right? I could keep going infinitely many fractions lower, so I can't really state a minimum. Yeah? Okay, that's why. Good question. Okay, are you guys ready to learn some stuff? Yay! Okay, today we're going to focus on how to find critical points. Okay, hey, so this is a big topic in calculus. And this whole chapter kind of sits on this, Okay, so this is like the foundation and the jumping ground for this chapter. So later on, I'm going to ask you to find relative extrema given an equation, and you have to use your calculus skills to find that. So the first thing we need to do is we need to know how to find these things called critical numbers. Okay? And you can fill in the blanks with me here. Extrema will have to occur either at an endpoint or a turning point. We know the endpoints because we're going to be given those, right? Those are going to be given. But the turning points, where are the turning points on the functions? The maxes or the mins. Your derivative, the slope of the tangent. Oh, we didn't talk about the slope of the tangent line at those numbers. Let's do that real quick. I'm sorry. Because that's what I want you to know for this line. That's good that reminded me of that. So, ladies and gents, what's the derivative at x equals -3? F prime of -3 is F prime of -3. DNE, right? It's a sharp point. And what's the derivative at -2? F prime of -2 is 0, right? And same at 1, F prime of 1 is 0. So my point, and nothing, don't worry about anything else. I only wanted to do those points. So my point is, we will have critical points where the slope of your tangent line is equal to 0, or that means we're taking the derivative, you can fill that in, and setting it equal to 0. These x values are called the critical numbers, okay? So basically, you find your derivative, you set it equal to 0, boom, those are your critical numbers. That's all we're going to be working with today, and then later on I'll show you what we do with it. Okay, so a visual, you can write this down with me. And I don't know why it's taking so long. There we go. Okay, so remember, we're going to have two types of critical numbers. The first type is when your derivative equals 0. So for example, if you have a graph that looks something like this, okay, your derivative is 0 there, right? Actually, I'm going to say what you'll see like in a calculus book is like f prime of c for a constant, and they'll put like a c here. That's for any like x value, like 1, 2, 3, 4, right? So at c, f prime of that constant is going to be 0. The second option is when the derivative is undefined, okay, or DNE does not exist. So in other words, there's some discontinuity, okay? So what that would look like is a sharp point, or, right, so if you have something like this, this is f prime of, like at this c value, f prime of c would be undefined or does not exist at a discontinuity, okay? So those are the two types. So basically, our discontinuity types, if you don't know these, write these down. Discontinuities are, can you list some with me? What do we know? Types of discontinuities. And I already said sharp points, so sharp points, hole, jump, asymptote, yep. Anything else? That's it. Okay. So just remember this, if you have any kind of discontinuity, then that's where you're gonna possibly have a critical number, okay? Typically that algebraically that turns into, hey, set the denominator equals 0. So here is, I want you to make a note card. You guys need another note card?
Yes.
So tonight, that's part of your work. Make a note card. And again, like the reason I'm doing this is because if you're taking a calc class in colleges, these note cards should be really helpful for you. I'm trying to help you out, set you up to do really well in calc.
That's right.
So I would just put some critical, like the little box I have in your notes I didn't scroll up here. Like this guy up here? Yeah, so I'm gonna tell you a second. Okay, so what I would put on my note card is this stuff that I have in this purple box. I would put that on my note card just to remember that's how I find a critical number. I would also maybe select one of these examples here and put it on the back of it, just so you can see what it looks like to refresh your brain when you take your college calc course. Okay? If when. Okay. So, no, it just depends on your major. I think for the majors that when I surveyed about the majors, I think almost, I think 13 out of 16 of you will need it for your majors. So, anyway, but yeah. Oh, okay. So, and honestly, like you need to know how to find your derivative and use your algebra skills to find zeros. That's it. That's really it. But there can be some tricky ones. So I'm going to say this is going to be like some of your homework for tonight. So let's go ahead and do some problems together. We are going to take the derivative. You can fill in the blanks on your note sheet there if you haven't yet. Do I have blanks there? Did I? Oh, no, I wrote them in. Okay, good. So we're going to take the derivative, set it equal to 0 to find critical numbers. Okay, now if you have a fraction, which you might not, if you have a fraction, set the numerator equal to 0 to find where f prime is 0. That visual up above that flat line. If you have a denominator, see where the denominator is 0, and that means your function is undefined, right? Because we can't divide by 0. All right, so those are all possible critical numbers. Okay, so let's try example 3. This is going to be an easier one. But before we begin, I always ask myself when I see a calculus problem where I have to take the derivative, is there any algebra that would make the calculus easier? And the answer to this, bless you, is, bless you times 2. Yes, what could I do here to make the calculus easier? Distribute. Otherwise, I would have to use product rule, right? Gross. So, yeah, that would make it worse. That's really funny. I love that you realize that, but I love that you saw the difference in squares. I'm so proud. So I would say, hey, f of x is x to the 4th minus 4x squared. And then it's just power rule. So now we take the derivative. We're finding a critical number by taking the derivative first, 4x cubed minus 8x. And then what do we do to find a critical number? We set the derivative equal to 0. It's easy. I really like this section in calculus. I really liked this chapter when I was taking calculus. I think it's more concrete than a lot of the stuff that you learn in calculus, but okay. So how do we solve this? Take out a GCF, right? 4x. Good. We get x squared minus 2 equals 0. Okay, set each factor equal to 0. And x equals 0. Ooh, x squared equals 2. What does x equal here? Root 2? Did I do that right? No. Yeah, good job. Plus or minus. Don't forget your plus or minus. So you can have critical points at plus or minus 2. Okay? Do me a favor, get out your graphing calculator with me. And I just want you to be able to see what's happening here. So your critical numbers are x equals 0 and plus or minus root 2. Okay, let me show you what's happening on the graphing calculator here. Later on, I'm going to have you use the critical numbers to identify absolute extrema. So if we go ahead and graph, x to the 4th, you graph the original function, x to the 4th minus, oh, that's weird. I never did that before. Minus 4x squared. Okay, it looks like this, right? So do you see how at 0, that's a critical number? Do you see 0 is going to identify your maximums? Check out this weird business here. This is at negative root 2. Negative root 2 and positive root 2. They identify your minimums, right? So that's kind of what we're going to be using eventually. But right now you're just finding critical numbers. All right. Next one. Okay, find the critical numbers. Take the derivative. What do I use? What do I use here? Quotient. Yep, quotient rule. The thing where you square it. Nice. That sounds like an episode of Friends. The one where you square it. Okay, S prime of t is low d high minus high d low 2t all over the square of what's below. Okay, I want you to notice something. Do you see how I put that numerator in parentheses? Right? Be careful with that. And then we have, okay, I want you to tell me if I'm doing this right or not. Okay? Did I do this right? Yes, do you guys see that I missed the negative distribution? That is a common problem. If you miss, you're actually distributing a negative 2t to both of those. So this, you see where I had the plus 6t? That should be a minus. So make sure you are good. Come on, technology, catch up. Come on, do your thing. This should be a minus 6t, and it will be changed when, maybe if I scribble. Oh. Ah, it's not working. Okay. All right. Next, we simplify this. We get negative t squared minus 6t. All over t to the fourth. Okay, ladies and gents, do you see that I can reduce everything by a factor of t? Negative t minus 6 over t to the third. Agreed? So negative 2t squared plus t squared. Yep. Good, good, good. Okay, do you agree with me on this last thing? Negative t minus 6 over t cubed. Right? I divided a t into each one. I canceled out a t for each term. Okay, so now set it equal to 0 to find your critical numbers. Okay, now watch this. To find where s prime, the derivative, s prime of t equal, we have two sets of critical numbers. Where the derivative is 0 and where the derivative is undefined. Woo. Okay, so we set our numerator equal to 0 to see where the zeros are. So you get negative t equals 6. You get t equals negative 6, yes? Come on, scroll up. Okay. Over here, where is the denominator undefined? I set t cubed equal to 0, right? Because we know the denominator can equal 0. T equals 0, cube root of 0 is 0, right? So my critical numbers are 0 and negative 6. That's it. Yeah. So anywhere something is undefined or where the derivative is 0, that is a possibility for a critical number. All right, let's try another one. Okay. I shall wait for the processing to happen.
So our final answer should just be critical numbers equal.
Mm-hmm. Yeah, I'm just having you right now identify the critical numbers. Okay, ready for another one?
Thank
you.
Okay.
Okay, so what rule in example 5 will we have to use? What rule in example 5? Product. Anything else in example 5? Chain. Now. So good at this game. What capital do you use? Okay, so I'm gonna rewrite this as x times 16 minus x squared to the 1/2. So do you see, first I need to use product rule because there's two different functions there. And then I need to use chain rule. Hey guys, there's a lot of chatter happening. Can we just, but I know it's Friday, but we need to focus, okay? So there's also chain rule because I have anything raised to a power other than 1 is chain rule, okay? So we're gonna do, let me write out product rule. So for g prime of x, we do first, d last, which is going to be x times, okay, now we got to take the derivative of this quantity to the 1/2. So that's going to be bring the power in front, right? 1/2 times what goes in the quantity? And it's raised to the negative 1/2. Subtract 1 from the power and times the derivative of what's inside, so negative 2x, right? That is the derivative of the last, all of that. Remember, for your chain rule, u to the n, the derivative of u to the n is n u to the n minus 1 times u prime, okay? That's first d last plus last d first is going to be the plus root 16 minus x squared. I leave it as a radical because then I don't have this, less I have to rewrite. Last times the derivative of the first is 1. It's catching up. There we go. Times 1. Okay. Nice. All right. Let's simplify. Ooh. Okay. What does all this business simplify to? 1/2 x times negative 2x. X. Do you guys agree? Yeah. So if I cancel the 2's and yeah, so I have a negative, and what happens to those x's? Squared, okay? So negative x squared. I know, the negatives they're tricky. So negative x squared, where does this 16 minus x squared to the negative 1/2 belong in the denominator as a square root 16 minus x squared? Does that make sense? Good there? Because really, to make it positive, it'd be 1 over quantity 16 minus x squared to the positive 1/2. Bringing a negative exponent to the bottom makes it a positive, and I'm just going to write it as the square root. And then finally, plus root 16 minus x squared. Okay, now this is g prime. We need to find the critical numbers. So set it equal to 0. How would you guys find the zeros here? Any takers? You could do one of two things. You could subtract that square root over, multiply by the other square root, or I think one of the easiest things to do, find a common denominator. Does that sound good to you? That's what I would do. So I would just put this over 1, and I'm going to multiply it by, it's missing the root 16 minus x squared, right, in the denominator. I'm going to multiply it by another root 16 minus x squared over itself. What's great about that, guys? It cancels, right? The root cancels with the root. So it becomes just 16 minus x squared. Okay. So I get g prime of x is negative x squared plus 16 minus x squared all over. I have the same denominator, so I can just write it as one denominator. Okay. Oh, I don't know why. Okay. So then, I get in the numerator negative 2x squared plus 16 all over my denominator. Thank you, yeah. Okay. And now I need to do two things, right? I need to find where my derivative, the numerator is 0 and the denominator is 0 where it's undefined, right? Those are my two ways I can have critical numbers. So where is the derivative 0? You set the numerator equal to 0. Where is the derivative undefined? Set the denominator equal 0. So my numerator, negative 2x squared plus 16 equals 0. Sorry. Okay. You get x squared equals minus 16 divided by negative 2 is 8. Take the plus minus square root. What is that simplified to? Root 8 becomes 4 times 2, 2 root 2, right? 2 root 2. So that's that. That was my numerator equaling 0. Then I take my denominator to see where my function is undefined. So I say, where does root 16 minus x squared equal 0? Oh, we square both sides to get rid of the square root. Or think of it as raising it to the reciprocal power. It's raised to the 1/2, so you won't raise it to the 2, right? You square it. 16 minus x squared equals 0. What does x equal? Don't forget your plus or minus. Yep, plus or minus 4. So I have 4 critical numbers here, right? These are all my critical numbers. The critical numbers are where you will possibly have maxes and mins. Do you have to have a max and min? No, not necessarily, but if you have them, they will be there, yeah? Or at your endpoints, okay? So do you want to see how you handle this one initially? Oh, wait, we don't have a lot of time. No, we're not saving this for Monday. We're gonna do it.
Get the limbs. loose.
Example 6. Oh, did I? Yeah. Let's do a trig one.
We should just skip over to number 7.
Skip to number 7. No, that's trash. Hey, also, I am giving worksheet. What is it? Where are we at? 3.1, worksheet 1 as homework. I don't think there's a ton of problems on there, is it? It's just one page, yeah. So, we'll see. Let me do this example though, okay? All right, first thing, do you guys see this sine squared? Let's focus. Do you see the sine squared?
Yeah.
I'm gonna rewrite it as sine x quantity squared. Tell me why. Tell me why.
It's easier to derive.
It's chain rule, right? So f prime of x is going to be bring the 2 in front, keep the same quantity, reduce the power. So to the first. You don't have to write to the first power, but I'm being extra clear. Times the derivative of what's inside, right? U to the n minus 1 du or u prime. Derivative of sine is cosine x. Let's see if you remember your trig skills. Oh, I'm sorry. What's I have to derive this the other sine x. It becomes cosine x. Derivative of sine x is cosine x as well. Okay, set it equal to 0. So I basically have 2 sine x cosine x plus cosine x equals 0. What do I do? Try again. Because if I do that, I can't divide and cancel trig functions. Remember, they lose solutions. I'm doing this in my trig classes now, actually. We're solving trig equations. What do I do instead? Think algebra. Try again.
Where I happen to be 2.
Factor. There we got it. I knew we'd get there. GCF, right? That's one that everybody forgets. Okay. So we're going to factor GCF, good old algebra. They always say students don't struggle with calculus, they struggle with the algebra and calculus, right? Yeah, I'm doing it with them. 2 sine x plus 1.
That turns into cosine.
So then set them equal to 0. Where does the cosine equal 0 on the unit circle? That is on your formula sheet. Do you remember cosine is x, sine is y?
Yeah.
Cosine is 0 at pi over 2, and where else?
Oh.
3 pi over 2, right?
Oh.
Okay. Where does the sine equal negative 1/2? Tell me one angle. Sine equals negative 1/2.
2 pi, 3.
2 pi over 3, do you guys agree?
Hopefully.
What is the sine value, ladies and gents?
Wait, it's a.
Y.
Y.
So that's the x. Try again. Okay.
5 or 6.
11 pi over 6? Do you agree?
Yeah.
Yes, I agree. And what other one? What other one? 7 pi over 6. Okay, so those are your solutions. Okay. There's nothing undefined for sine and cosine. It's always negative 1 to 1.
Okay, so for the last example here, example 7, S of t is a quantity raised to a power. So that's going to be the chain rule, right? We need to derive it. So we're finding the critical numbers. And remember, you take the derivative, you set it equal to 0. Any denominator that equals 0 is undefined where the derivative does not exist. So we have to list those as critical numbers as well. So we're going to find S prime of t, bring the power in front. Write the same quantity. Subtract 1 from the power, negative 1/3. And then times the derivative of what's inside, which is 1. And then simplify. I'm going to get rid of that negative exponent. So remember, negative exponents become positive when you move them to the denominator. Right? You could have immediately written that as 2 over 3 times the cube root of t plus 2 if you prefer. Okay. Then to find critical points, I take my derivative, set it equal to 0. When the numerator equals 0, that's when, I guess it's not f prime this time, it's s prime. The derivative is 0, right? Our tangent line is 0, typically at a max or min. So we're going to say, well, to set the numerator equal to 0, 2 can never equal 0. So there are no critical points there where the derivative is 0. However, the denominator can equal 0. When the denominator equals 0, that means the derivative, in this case s prime of t, is undefined or it does not exist. So we're going to say 3 cube root of t plus 2 equals 0. Whoops. And then divide by 3. You have the cube root of t plus 2 equals 0. If it helps, you can rewrite this as t plus 2 to the 1/3. That might help you solve the equation. Whenever anything is raised to a fractional power, you raise both sides to the reciprocal power, right? So we're going to raise this to the 3 over 1, or just cube both sides. That's how we get rid of a power, right? So if it's like x to the 5/6, right? You raise it to the 6/5, right? And pop it in the calculator, okay? So continuing here, we get t plus 2 is equal to 0 cubed is still 0, t equals negative 2. This is our only critical number here. Okay, and that is it.